Hey everybody, how are we doing? We are starting to go now into our next chapter here. We are in 4.2 and 4.3. It's two sections together at once. We're looking at now starting to see patterns in these. We kind of saw some of it when we were doing our last lesson, but when we start looking at graphs and we start looking at table of values and things, we can start to see patterns and see how is the graph changing or how are our x's changing in that table of values compared to the y's, and start to notice some patterns. And once we see particular patterns in math, it gives us clues as to what's going on. So what we're going to start with is, what is a linear function? First off, let's think of a few things. We talked about this. A linear function is a straight line. It also, if you notice, why is it straight? Because that change that's happening in our y's, the change in y's, compared to the x's, constant. So yeah, a linear, when we look at it visually, it is a straight line. And then when we look at it in a table of values, you'll start to see, hey, what's happening to the x's, what's happening to the y's, and when we compare them, it's a constant change. And we can notice that as we just see how these numbers start to increase and decrease. Two ways that we can see these, of course, we just talked about it a little bit, graphically and computationally. Graphically, as you see right here, right, we have two functions. This one here is clearly a line. Look, it is constantly changing. It's a nice straight line, well, as best as it can be to be hand drawn. This one is made up of a bunch of little straight lines, but together across the entire whole, they're not, it's not linear. It has changes in slopes as it's going from one section to the next. We can also look at this, like, look at this, from 0 to, if we carry this like right down, right? Trying to, again, I'm using a mouse, trying to do the best I can. From 0 to, I would say this is probably like 1 1/4. From 0 to 1 1/4, this graph is increasing. It's going up. And then from 1/4 to, carry this straight on down. I guess this would be like 2.5. From 1.25 to 2.5, there's no change. There's zero change. See, it's a horizontal line here. So it's not increasing and it's not decreasing. It's kind of just stalled. There's no change here. No change. Then look again, if we were to continue this, if I'd say here's maybe like, let's do 3, 4. Take this. Again, from this point, from 2.3 to 5, it's increasing.
Parent conference in E7. I need Mr. Carlisle, Mr. Bishop, Mr. Hopp, and Ms. Fallon to go to E7 for your parent conference. Thank you.
Sorry about that. Announcements at school. Not much I can do about it. So yeah, again, 0 to 1.5, we have an increasing. So from 0 to 1.5, it's increasing. It's not, there's no change whatsoever from 1.25 to 2.5. And then from 2.5 to 3, it's increasing again. And then here on out, again, there's no change, no change. All right, how do we look at this? Maybe when we look at, they want to know which one of these is linear, why? But we're looking at a computational side of it where we just have a table of values. Well, let's look at the x's. So the change here is what? 1. From 1 to 2 is a change of 1. From 2 to 3 is 1. 3 to 4 is 1. That's pretty constant. And when we inputted these, what's happening with this change? It went up by 2. And this increased by 2. This increased by 2. It increased by 2. So here we go. Look, as each x increases by 1, the y's are increasing by 2. This is a constant rate of change. This is linear. Linear. Anytime you see this happen where for each value or increment of x, if it's the same as it is with the y's, you have a nice linear line. That will make a straight line. What about this one? An increase by 1, increased by 1, and increased by 1. Hey, that looks great. This went up by 2. Then this went up by 1. Then it went down by 5. Notice there is no consistency in this side. This is not linear. All right. And why is it? Because these have a constant rate of change. This is all over the place. It's going up, down, and then it really jumps down even farther. The decrease is not even. So when we want to look at this again, how do graphs change? How do graphs compare? We're looking at these intervals here, guys. Look, this bottom graph here over the entire graph, over its entire interval, is constantly increasing. While again, as we talked about in this graph, if we're comparing, look, each segment of this graph from here to here is one. It's a segment that's increasing, that's staying the same, then it's increasing and staying the same again. So we have to look at these and say, okay, increasing, is each section increasing or decreasing? What values of x are they increasing? We said from 0 to 1.25 was increasing. Then that was no change in between this, increasing, and then from here to infinity it seemed to be going up forever because the arrow pointed up that it was just going and going and going and just doing its thing. No change forever and ever and ever from 3 to infinity. Now we also have some interesting things here. We have talked a little about this, right? Independent variables in particular are our x's. Okay, they're also our inputs. And of course, they are anything that we notice when it's on an x-axis. Because if we're given a graph, we look at that and it is our x-axis, is all of our independent variables. Again, this in so all of this means the same thing. They can interchange any of these words at any time. X's, inputs, the x-axis is our independent axis, independent variables, all that is all interchangeable vocabulary for us. In turn, we have dependent. So dependent are our y's. They're the outputs. Y-axes. These are all our dependent variables. Now, sometimes, guys, we're given these table of values, and we look at it, and they want us to graph this. I'll zoom out so I can see better in this graph. But we have to create scales that are margins so that they are appropriate. Look at this. So these number of pounds, if you're looking at this, the number of pounds determines the price, right? You look at these because you got to figure out which one is the x's, which one is the y's. So here, x's, number of pounds. The y's is total price. You're going to almost notice always that total price will be a y. It's a dependent. You don't know what your price is until you figure out how many pounds you're buying of something. And our pounds are going by what? 10, 15, 20, 25. So they're going by 5. So you want to make a scale. So 5 starts, of course, 0, 5, 10, 15, 20, 25, and we're hand graphing, so it's pretty accurate for a hand graph. Total price is going by looks like 20s, right? So 0 to 20, and then 40. 60, 80, let's do 100 for fun. All right, going up by 20s. Here's price and pounds. And these are ordered pairs. So when we sell or we have purchased 10 pounds of whatever this is, we in turn are what? Spending $20. X is 10, then you go up to 20. Next one, 15, be 40. And then 20 would cost us 60. 25 would then cost us 75. Look at that. That is definitely not a linear function. Notice it looked like it was going to be, but then we started doing what? This was in line with this, which was in line with this, but then all of a sudden at 25, something changed. See the difference? From here to here difference was 20. There to there, the difference was 20. Here to here, it suddenly changed to 15. Maybe whatever we're buying, there's like a price break, right? Once you buy 25 pounds or more, they start charging you only $15 a pound. You don't know. But what we can do is we can look at the information they give us. You can put it onto a graph. You can analyze this change, because these are all changing by 5-pound increments. I put it on a graph and we look, hey, this is not lining up. This is not linear. All right, different ways that we can look and observe things. Here is another graph that they gave us. And let's just see, can we figure out anything about this? This is going up by what, 3? This is going up by 3. It's going up by 3.5. 1.5. The difference here is 1.5. I can tell this is linear. It's linear. But if we were going to graph it, we just got to be careful when we graph these, right? We can do it in a multitude of ways. Our y's, I'm just going to go like 1, 2, 3, 4, 5, 6, 7, 8, 9. 9.5 would be up here. All right, so these are the x's. Across here is your x-axis, your y-axis. And I did everything by ones, just for fun. So we go to graph these, what, 3, 5. And then we did 6, 6.5. Somewhere in between these two. We're going to try to draw that line back, right? 9. It should be about 8. And 12 is probably right above our threshold there. Didn't do a great job on the margin. I could have squished that in a little, but look, see how it is forming a line. So this is definitely a linear representation. Now here's the cool thing. I mean, look at this. These didn't have like initial values or starting points, but we talked a lot about this in the last thing. When our x is 0, right? Could we predict going backwards? I could get a point before this, right? This is changing by 3. So if I go backwards by 3, so I'm taking this to 0, and I'm going to take 5 and subtract the 1.5, right? I end up with 3.5. Notice, see how that it falls in line? You can predict this. Whenever x is 0, that is your initial value. Or your y-intercept, because that is the point at which the line, actually is intersecting. That is super, super important for us to be able to do, because not all table of values start with 0. But if we can see this linear pattern of the 1.5, right, we can track our way backwards and get that initial value. Which brings us to this last example here. Here's a bunch of ordered pairs. 0, 2, 1, 4, 2, 6, 3, 8. I'm going to challenge you here to let's represent this differently. Let's put this in our table of values, right? The XY table of values. Let's set our ordered pairs up. 0, 2, 1, 4, 2, 6, 3, 8. And just by looking at this, now that we've taken it from ordered pairs and put it back into a table of values, can we start to see a pattern here? Goes up by 1, goes up by 1, goes up by 1. I definitely see a pattern. Look, this goes up by 2. This goes up by 2. This goes up by 2. Right? And I definitely see an initial value. Look, here's an initial value, our x, when our x equals 0, there's an initial value. And it says write an equation that represents this, right? If you can see an initial value, what do we need to do this? We need an initial value. So what is the y when our x is 0? What is y? That's our initial value. It's the y. And we know that is what? Looking at our chart, we can say, hey, I can see this. I see it's 2. Then the other thing we need is we need to be able to tell, well, what is the rate of change on the y's? Look, whenever x is changing by only 1, and you see y is changing by the same amount, that is your current rate of change, so to speak. And this is as simple as it gets, okay? Notice the x's are changing by a rate of 1. So the y's are changing by 2 each time. This allows us the opportunity to be able to write an equation for this. And this is all we do. So we have our y is going to be equal to, well, what is this change of x? We need the changes that are happening. The x is changing by 1. So when the x changes by 1 and your y's are changing by the exact same amount, we need that 2. The 2 is important, so we use the 2. We do 2x. And then whatever our y-intercept is, well, we said our y-intercept was what, 2? So I have to type that in or it's not gonna. So yeah, our y-intercept was a 2, so we can put a plus 2. And that is this equation. We can test it, right? 0, plug in a 0. 0 times 2 Yeah, that's true. We'll do it again for 1. Well, 2 times 1 is 2, plus 2 equals 4. Yep, you do it again, and you can keep checking it with what they gave you, okay? So as you sit here, you're starting to notice patterns, these patterns that form in our linear equations and nonlinear equations. There are some sort of nonlinear equations that we start to see a pattern form in them as well. Right now, we're focusing more on the linear side, but as you go through and you see all these changes, and as long as you can say, hey, I can see an initial value here because they gave it to us, or maybe you can recreate this initial value. We can start to see this interesting pattern that's going on, and then be able to maybe even possibly create equations. When we see these, it's not outside of our scope. We were able to graph them. You can graph it and see, hey, look, it appears to be linear. But then as we started looking at the last point in this one, it changed. It ended up not being, because this change in y's was different compared to our change. While you had a constant change in x's, the change in the y's was not the same, and so on. And we learned that we have independent. Independent could have many different names for it. X's, inputs, x-axis is independent variables, while dependent could be our y's, our outputs, the y-axis, and dependent variables. We learned about intervals, that as different graphs change on intervals, you have increasing. There's no change. We didn't have any decreasing, but if this went down this way, that would be a decreasing interval. So we just think about this as we go. And again, computational graphing, sometimes we need to put these things into a T-chart to help us be able to solve. Make sure you're getting out there, finish that homework up, guys. Have a wonderful day today.